All right, so we're going to cover the rest of Chapter 2 in this slideshow, this video. And if you remember, in the last video, we looked at how mirrors form an image. And in this video, we're going to look at images formed by both converging and diverging lenses. We're not going to look at images formed by refraction. So I think that's section 3 in your chapter. Again, this is just really for time's sake and to cover the most meaty material in the chapter, or the ones that I think are going to be the most useful for you. Unfortunate, but I just think in order to also move on to the next material, that'll be the best choice. So basically a thin lens, and that's what we'll be concentrating on, has two surfaces where light is going to refract, both when the light comes into the lens and when the light leaves the lens. And the idea is that that refraction, or that bending of the light, will be hopefully done in a way that will bring the light together to form an image, although there are other times when we actually don't want the light to converge because we do have diverging lenses. So let's look at the two types of lenses just to get a sense of the visual of what they look like. So we classify lenses either as converging or diverging. And as we'll see in a minute, that means like what they do to light that comes into them. Do they bring it together, or do they cause it to sort of spread out? The top row, you see the converging lenses. And one of the things that is pointed out, that the middle of a converging lens is actually fatter than the top and bottom. And that's one of the ways that you can tell by sort of feel if you're given a lens. Diverging lenses are the second row, and those are actually thinner in the middle. Okay, so here's a picture that illustrates what we mean by converging and diverging lenses. So we sort of start off with light coming into the lens where all the light rays are parallel to each other. And for a converging lens, these light rays are going to come together and intersect at a single point. When you do set it up like this, we're looking at the light converging at the focal point, and then the distance from the lens to that point is called the focal length of the lens. In the second picture, we see the same thing, but with a diverging lens, and this might remind you of mirrors because it is very similar, except that we're refracting and not reflecting light. So the parallel light rays come into the lens, and because it's a diverging lens, the light rays over here aren't coming together or intersecting, but if we trace them backwards, it appears that they came from a common point, and that's called the focal point. For that diverging lens, it's actually in front of the lens. Just something, I think I'll probably mention that later. For the converging lens, that means that this focal length is a positive quantity, but for the diverging lens, the focal length is a negative quantity. Okay, so let's take a little bit closer look at the thin converging lenses, and then we'll also talk about diverging lenses. We like to sort of think of the light and the focal points in two different ways. Because a lens actually can work either way. It's not like you can only send light through one side of it. It can go both ways. So there's actually a focal point in front of the lens and in back of the lens for each surface. And so this picture is showing that if all the light tends to originate at the focal point in front of the lens, when it passes through the lens and is refracted, it'll be bent in a way so that the light rays that emerge from the lens are all parallel to each other. And so again, the distance from a lens to the focal point is called the focal length. It's a very important quality of a lens. It basically allows us to determine, what kind of image it's going to form. And for instance, in a telescope, your focal length will help you determine how large your image is going to be. And so you can choose your focal length to get the type of image that you want. Now, just as we said, if the light originates at the focal point and goes through the lens, it'll emerge parallel. We can do the opposite thing. If the light rays come into the lens in a parallel path, when they bend as they pass through the lens, all the light rays will converge and intersect at the focal point on the other side. I liked this picture. I thought it was kind of cool because it also had sort of application. So this was really like the picture that we showed originally where the light was originating at the focal point. And so they're saying here, if we took a converging lens and we put a light source at the focal point of it, when the light rays come out the other side of the lens, they're going to be coming parallel to each other. And they're pointing out that this is a way that we can make a directional beam of light, like a beam of light that we can aim, and you could use that for a traffic light or a lighthouse. Now the diverging lenses, as we saw before, diverge the light. So here's a picture again, sort of similar to what we saw before. When the light rays are coming into the diverging lens and they're parallel to each other, when they pass through the lens, they'll spread out, but if we trace them back, they appear to originate at this focal point, and so that would be the focal point for that lens. And actually, the difference between this is that, in a sense, this focal point right here that we see, that I've highlighted in blue, is the focal point or length for the second surface of the lens, where this one right here would be the focal length for the incoming surface. And as I mentioned before, diverging lens will have a negative focal length, and that becomes important later on. We also find that, now this is a little bit more complicated, working with diverging lenses always takes a little bit more thought. Instead of the light rays appear like having originated at a focal point, these light rays are coming in, but they're all spread out. But notice, if we extended them to the other side of the lens, they appear to have they would all go towards this focal point, which is the focal point of the first surface. So if we draw those light rays like that, when they emerge from the diverging lens, they'll all go parallel to each other. Okay, so here is a picture of a converging lens, and here we have the object for the lens, and notice the focal point is shown, and also notice this is the distance from the object to the lens, and then over here we have an image, and notice that they drew some light rays. And I did upload some older videos that I did that talked about how to draw ray diagrams. So if you are interested, you can watch that. But these three main light rays are drawn in a very specific way that I describe in the video. And what happens is you notice that when they all intersect on the other side of the lens, and so since they all originated at the tip of the object, this is where the tip of the image would be formed. Interestingly, notice the image is inverted, and that is a characteristic of the converging lens. Because of the fact that the light passes through the lens and then converges to form an image, means that that image is real. I like to always classify it as it's on the expected side of the lens, and so that's what makes it real. This kind of image, when it's real, has a positive image distance, which is shown right here. And again, just to remind you that because this is a converging lens, the focal length would be positive. Now, this is the ray diagram for a diverging lens, and those ray diagrams are a little bit more complicated, but notice that, as expected, over here, all the light rays are sort of moving apart from each other. They are not going to intersect. But if we trace them back from where they appear to have come from, they do appear to come from this common location, and that is where an image would be formed, but that is a virtual image because of the fact that it's formed on the same side of the lens as the object. If you just think about how a lens is expected to behave, you would expect the image to be formed on the other side of the lens. That's where a real image would be formed. This one appears to be formed on the same side, and that's why it's a virtual image. Virtual image will have a negative image distance. That's what signals to you that it's virtual. So now here's just a comparison, sort of in the last two slides led us to believe that a converging lens will always give us a real image and a diverging lens will always give us a virtual image. Well, it is always true that a diverging lens will give a virtual image, but there is the possibility that a converging lens will give a virtual image, and that only happens when the object is closer than the focal length from the lens. So notice here, here's the focal point right here and here. And so we notice in this first picture for the converging lens, the object is further away from the lens than the focal point. But in this picture where we got a virtual image, it was actually closer. So we found that was true also for the converging or concave mirrors, is when you moved your object in really close to the mirror, it switched from being a real image to a virtual image. So putting all these things together, we have a pretty simple equation. Probably looks familiar because it's basically like the equation for mirrors, and it's called the lens equation. So d sub O, of course, is the object distance, d sub I is the image distance, and f is the focal length. Just so we're familiar with our sign conventions, f is positive if it's a converging lens, f is negative if it's a diverging lens. The image distance is positive if it's a real image, and the image distance is negative for a virtual image. Just to sort of clarify what we mean by real and virtual, the light has passed through the lens and converges to form the image. It's on the opposite side of the lens from the object. For the virtual image, the light appears to come from a common point on the front side of the lens. The image is on the same side as the object. Also have a magnification for our image, which is a ratio of the image height to the object height. Something I didn't mention previously. If the image height is negative, that means that it's upside down or inverted. And if the image height is greater than 0, it's upright. We can also relate the magnification of the image to the image distance and the object distance. So we have the total relationship here. Once again, if the magnification is greater than 0, your image is upright. If m is less than 0, your image is inverted. If the absolute value of m is greater than 1, the image is enlarged. And if the absolute value of m is less than 1, the image is reduced. And you'll see if those look familiar and sound like the conditions for the spherical mirrors. You're exactly right. They're exactly the same. And so that's what we're going to cover in this chapter. I just wanted to make one final statement that if you're interested in how you do ray tracing or ray diagrams with lenses, I had done a video a couple years ago for my class, and so I did post those on our chapter site. So that's it for chapter 2.